Hello everyone and welcome to Triple E 25. So our first lecture will be on probability models and axioms. So this will be the format of today's lecture. So we begin with a review of set theory, which will be essential in the discussion of probability models. The review would include defining what sets are and introducing the set of terminologies and notations that we are going to use when we are talking about sets. Also, we are going to talk about operations involving sets, and we are also going to talk about a tool that we can use to visualize sets and relationships among different sets. After the review, we're going to finally talk about probability models, and basically, a probability model is a mathematical description of a situation with uncertainty. Now, a probability model has two components, and we are also going to discuss that today. The first component would be the sample space, and the second component would be the probability law. So let's begin. What is a set? So, a set is a collection of distinct or well defined objects. So this is a mathematics course. Maybe you're thinking that the object or objects would only consist of numbers. So what would be a set that consists of numbers? Um, the set of all integers uh, from the interval between 0 and 100. So that is a collection of numbers. But the objects of a set are not restricted to numbers only. So we can also have, for example, the days of the week. So the objects forming that set uh, obviously aren't numbers. So we have Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Now, the technical term for the object of a set is called an element. So in my most recent example in days of the week, so Monday is an element of the set of the days of the week. Saturday is also called an element. Now we have a notation for that. Now suppose we have a set S, or represented by the capital letter S, and we have an object represented by a small letter x. Then if we say that the small letter x is an element of the set capital S, then we can use this short notation x followed by this e looking sign followed by the capital letter S representing the set. Now, if this is not true, say x is not an element of set, then we also have a notation for that. So if we want to say x is not an element of S, then we use this notation right here. So it's also an E, but there is a slash on top of it. So that means it's x is not an element of capital S. In some cases, a set would have no elements at all. And we refer to those sets as empty sets. And we also have a notation for that. So you can say that a set is empty by using this notation right here. So it's a circle with a slash on top of it. Or you can also alternatively use a pair of curly braces with no uh, object or element inside of it. Now, to describe a set or to specify a set usually involves describing the elements uh, that are inside that set. And there are a couple of ways of doing that, and that depends on the kind of set that we are dealing with, specifically on the kind of elements that belong to that set. So, one way of describing sets is by listing. So, this is the most straightforward way. And usually, we list down the elements of a set when we know that the elements of that set is finite. So for example, again, in days of the week, so we can just list down the 7 days of the week, Monday to Sunday. Another example would be to list down the possible outcomes in a die roll. So assuming we're referring to a six-sided die, so to describe that set, we just need to list down the numbers on each side of that die. So that's 1, 2, 3, 4, 5, and 6. Another example would be the set of possible outcomes in a coin toss. So that is actually a smaller set. Here, a coin toss can either end up as heads or tails. So if we describe that set by listing, so we have here H representing heads and T representing tails. Now, what's nice about listing is that it's a very direct approach to describing a set. Um, the downside of describing sets in this manner is that if the set has too many elements, even if it's finite, um, then you will have a difficult time listing down all the sets. You cannot also use listing when you have infinitely many elements in a set. And so in that case, you need an alternative way of describing sets, and that is via using a rule. So, how are we going to describe sets by a rule? So, let's have this example. So, here we have the set of all real numbers between and including 0 and 10. So, if you know what real numbers are, so obviously it involves not only the integers but also those with decimal numbers, so irrational, rational numbers. And even if you're considering a very small range, such as this one, between and including 0 and 10, we know that there are infinitely many real numbers in that interval. And we cannot use listing to completely describe the set. So we're going to use a rule. And how are we going to do that? Well, the answer is right here. So you have inside a pair of curly braces, say an element represented by small x, followed by this vertical bar here, and then the set of descriptions that must be satisfied by x to be able to belong in this set. So in our case, it should be a real number. So that is covered by the statement here. And then it should be inside the interval defined by 0 and 10, and including 0 and 10. So that is covered by this inequality right here. So how is this read? So you say x such that x is an element of the real number system and x is between 0 and 10 and may be equivalent to 0 or equivalent to 10. So the vertical bar right here is read as such that. Okay. So what are other notations that are commonly used when describing sets? So usually we are only interested in a certain set of outcomes, and we want to define a set that uh, contains all the possible outcomes of interest, then we are referring to a universal set. And for this course, we're going to use the big omega to denote the universal set. And once you have defined your universal set, then you can talk about subsets. And basically, so subsets would contain um, um, a certain pool of outcomes or elements, and that pool may not include all the possible outcomes inside universal set or some other bigger set. So for example, you have the numbers, the set of numbers or integers from 1 to 10. One subset would be even numbers inside the range defined by 1 and 10. So that is a subset. So our notation for a subset is as follows. So if we have two sets, capital T and capital S, and let's say T is a subset of S, so we can have a shortened notation of that. So it's expressed as follows. So you have capital T subset of capital S. Now, some would say that this is actually read as T is a proper subset of S, and that is actually the more correct interpretation of this notation. And basically, a proper subset, if you can recall, contains, so for example, S has 10 elements, then the set T would only contain less than 10 of those elements. So T there is a proper subset of S. In some cases, when now when you are referring to a set that is not a subset of S, so then we have this notation right here, similar to elements. So here you have the symbol for a subset with a slash on top of it, and this notation right here says that the set T is not a subset of the set S. Now, we can easily visualize sets and existing relationships among them using Venn diagrams. And I'm going to use these 6 sets right here to uh, enumerate the common operations involving two or more sets. So we start with the first image right here. So this one is a Venn diagram involving the universal set. So this universal set is this big rectangle right here. And here you see the notation for the universal set. And inside that universal set are two subsets. So set S and then set T. And the mathematical representation or notation for that is these two statements right here. Now, let's try to describe the relationship between the two sets S and T. So you can see that you can interpret it as follows. So there are some elements in S that are also in the set T, but not all of them. And this shaded region right here refers to the intersection of two sets S and T. And the notation for the intersection is this image right here that looks like in an inverted U. So, and when we say intersection of two sets, and we are referring to elements that are both present in sets S and T. Next, if there's an intersection of two sets, there's also a union of two sets. And the notation for the union is the upright U. So when we say S union T, then we are talking about elements that are present in S or T or in both sets. And if we are going to use a Venn diagram to visualize that, then you will have this image right here. So the shaded region consists of all elements in S and all elements in T, and obviously that includes elements that may be both in S and T. Complements. So complement of a set is denoted as the set that we are referring to followed by a superscript C. In some books or in some textbooks, you have a prime or apostrophe symbol, but for this class, we're going to use the superscript C to denote the complement of a set. And when we are talking about the complement of a set, then we are referring to elements that are not present in that set. So for example, in this Venn diagram right here, when we say the complement of S, this is read as the complement of S, then we are referring to this shaded region right here, which is outside set S. Now if I say the complement of the set T, then the shaded region becomes bigger and it will now include this area right here, just outside this small oval that represents the set T. Other relationships between sets that we can derive from this Venn diagram is as follows. So T is a subset of S. So here we see that all of the elements of T are also included in S. So alternatively, we can also say that T is a proper subset of S. Let's have a quick exercise. Can you describe the shaded region using set operations? You can click pause and attempt to answer this question right here. Or if you just want to know the answer right away, so I'll give it to you. So did you answer this one? S, the intersection of S with the complement of set T. So if you answered this, then you are correct. So let's try to check why this is the answer. So what is the uh, complement of T first? So this is T. Now we say that the complement of T would involve all objects or elements that are not in set T. So that would mean shading this entire region right here and leaving this oval right here unshaded. Now set S would refer to this oval right here, and if we get the intersection of S and the complement of T, then we are referring to elements that are present both in S and the complement of T. And we know that the intersection of those two shaded regions would be this gray, darker gray area right here. So that's why this is the answer. Okay. Finally, so we've talked about intersection, union, complement of set. So another terminology associated with sets is the concept of disjointness. So here we have disjoint sets, and basically disjoint sets are sets with no common element. So specifically, a set, uh, basically if you have sets and they are said to be disjoint, then any pair of set will doesn't have a common element. So for example, in this Venn diagram right here, you have three sets. S, U, and T are disjoint sets, and we can check. So S and T don't have an intersection. It's an empty set right here. The sets S and U doesn't have an intersection as well, so it's an empty set too. And the intersection of T and U is also an empty set. So since we have satisfied, we have proven that these three would result to an empty set, then the sets S, T, and U are disjoint sets. An extension of disjoint sets would be a partition. And here, a partition of a particular set A would involve a collection of disjoint sets. And when we get the union of those disjoint sets, what we get is the set A. So if we apply that definition to this Venn diagram right here, then we have three disjoint sets, S, T, and U. If you get the intersection of any two sets, you will get the empty set. Now, the sets S, T, and U is a partition of the universal set omega. And you can verify that easily by getting the union of S, T, and U. And you can see that ST and U covers all of the elements inside the universal set. So ST and U is a partition of the universal set omega. So that's it for the review of set theory. The next leg of the lecture we will be talking about probability models and its components.